Respected participants, a very warm welcome to GIMA webinar. We are privileged to have among us Mr. Chris Richard from LALLEMAND Biofuels and Distilled Spirit as a speaker from industry. Mr. Richards has over 4 decades of experience in brewing, distilling, and biofuel industry, including role in production, sales, and management. He earned his bachelor degree in brewing and biological science from Hertford University in Scotland. At LBDS, Chris oversaw international sales and business development of fermentation ingredient for biofuel and distilled spirit industry for more than 15 years, but now has transitioned into a business development consulting role for LBDS. He is also a distinguished speaker, having presented at numerous events in the USA and internationally, and has authored scientific articles as well as 2 chapters in the 6th edition of the Text Alcohol textbook. I would now like to invite our knowledge partner to start knowledge share. So over to you, Mr. Richards.
Thank you.
Welcome, sir.
Good afternoon, everyone. Today's topic is about Biotech Yeast, a game changer. It's something that I feel very passionate about for India. I think it's the way forward, and you will see from my presentation why I think that. Okay, what is biotech yeast? This is a yeast that has been modified using advanced genetic engineering techniques. Generally, there are 2 categories of this. The first one is where no external DNA has been introduced, but increased or decreased expression of existing traits. So something that you are looking to either improve or reduce that's within the yeast can be overexpressed or underexpressed. The second category is external DNA is introduced to add a specific new trait. This is where, for instance, you find a trait in a bacteria or another yeast. In the particular case that we're interested in at the moment, this is the expression of glucoamylase, and then that is introduced to add a specific new trait. So what is no external DNA? This can be called gene tweaking. And as I say, we've already talked about this, and it can overexpress or underexpress roles. It can be used to change existing metabolic pathways within the cell to turn on or turn off those pathways. It can be used to reduce glycerol or overexpress beneficial congeners, such as this for distilled spirits. So if you want improved esters, you can overexpress ester formation. This is the traditional GMO. And so it takes identifying the required trait in another organism, extracting those relevant genes and inserting the gene into the target yeast. This is used to introduce novel non-Saccharomyces traits to allow new feedstock utilization, in the example of cellulosic or C5, new byproducts, enzyme expression or bioplastics, yield improvement, low glycerol, novel flavors, either smoky, high esters, or many others. In a lot of cases, though, there is a combination of these techniques used. So, for instance, once the new trait is introduced into the yeast, gene tweaking can be used to increase the effect or enhance it. An example of this is to introduce enzyme expression, such as the GA, and then overexpress it to reduce the required external enzyme addition, potentially all the way to 0. So what's happening globally? Already in North America and Brazil, the 2 largest ethanol producing regions, a number of years ago, the regulatory bodies implemented procedures to approve this technology. We spent a long time building the packages and the legal documents to apply for approval. And as a result, both industries are now utilizing to a very high level biotech yeasts and taking advantage of both yield improvement and process benefits. In Brazil, Brazil is utilizing biotech yeasts in both the sugar cane ethanol and the corn ethanol industry, but two very different yeast technologies. We developed for the sugar industry a yeast that could survive season-long yeast recycling because Brazil has this very, very unique methodology of centrifuging and recycling the yeast, and it creates a very, very high stress on the yeast. So we had to develop a yeast that was able to survive that, and this creates higher yields through reutilizing glycerol that has already been produced, thus not requiring so much glycerol produced and therefore producing more ethanol. In the corn ethanol industry, Brazil is utilizing a yeast that expresses multiple enzymes: glucoamylase, alpha amylase, proteases, phytases, trihalases, as well as converting some of the glycerol production into ethanol, thus increasing yield. This is probably the 8th or 9th version of these biotech yeasts since we started producing it initially 13, 14 years ago. And each time there is an improvement. In the USA, feedstock being almost 100% starch-based and predominantly corn, the main type of technology is very similar to that of the Brazil corn ethanol. So it's multiple enzyme expressions, glycerol reduction, creating increased ethanol. In the USA, I don't know the exact figure, but it is over 80% of the industry is utilizing biotech yeasts. This has become the predominant methodology of yeast handling in the USA. So what is the current situation in India? Over the last 18 months to 2 years, the Indian regulatory bodies set up the procedure for approval for biotech yeast for the production of fuel ethanol. Note, at this moment in time, it does not include utilizing these yeasts for potable alcohol or currently ENA. So working with GAC, you need to apply as a yeast producer to gain approval for your products or brand by supplying a package of information that shows the technology used to create the product, the safety information, the environmental information, the storage conditions and warehouse conditions, plus a number of other items, but these are the main ones. And following a number of meetings and questions, you hopefully gain approval as we have. Step 2, separately from the importation license, each end user has to apply for a permit for commercial use, including the description of use, the risk mitigation of the use of the material, and setting up a safety and technical committee. We've partnered with a number of customers to already have gone through this process, and once approved, we can then progress to a trial and commercialization. So why so complicated? With the number of differing states, it's important that an overall consistent approach to approval is achieved. It's also critical in the early stages of biotech implementation and approval across all industries that safety and risk mitigation are managed centrally. Please bear in mind that Saccharomyces cerevisiae yeast that we're using here is a biosafety level 1, which is the lowest level of risk. Obviously, if you are utilizing other organisms that are higher risk levels, more risk mitigation and safety methodologies need to be implemented. Also, due to the fact there are multiple industries involved, potable, ENA, biofuels, it's important to limit the use at this time to only to biofuels. So this is the reason for the end user application and approval, to ensure that it is only being used in the biofuels area and not in the sort of potential food or potable alcohol. So why am I calling it a game changer? Traditional ethanol production has both processes and biological limitations. Utilizing biotechnological techniques, these limitations or barriers can be removed or at least pushed back. So novel feedstocks, 5-carbon sugars, cost reduction, yeast enzyme expression, yield improvement, glycerol reduction. Please bear in mind that for every molecule of glycerol produced, you lose 1 molecule of ethanol. Novel enzymes, the proteases, phytases, trihalases, all of these help improve the process with reduced cost than compared to adding these things separately. The other one that's very important at the moment is alternative products and byproducts, moving into the bioplastics arena and other opportunity to produce other byproducts. In a number of countries worldwide, the ethanol blending and production capabilities are hitting the ceiling. So having alternative production that you can apply your process to will be even more important in the future. And these are just the current areas of research. Sorry, I'm seeing some scribbling on the screen. I don't know what's causing that. Current options being tested. GA replacement. This ranges between 40 and 100% reduction. Glycerol reduction from 20 to 30% reduction is claimed. And yield improvement from 1 to 3% yield gain. These are things that are being looked at within India at the moment with the current products that are looking for approval or already approved. Compared to globally, what is happening in the rest of the world? GA replacement ranges from 70 to 100% reduction. Multiple other enzymes are being expressed: proteases, phytases, AAA, alpha amylase, trihalases. Glycerol reduction, up to 60% or more reduction seen in the field. Yield improvement, up to 6% or more of yield gain versus conventional yeast. There are also other innovations being tested. Alpha amylase replacement. Now, when I talk about alpha amylase replacement, I do not mean in the fermenter. I mean utilizing yeast to replace the alpha amylase that is currently purchased and utilized in the liquefaction. This, we believe, is a potentially cheaper option, lower cost for enzyme addition. Other ones are antimicrobial replacement. So the yeast could produce a non-antibiotic methodology of limited antimicrobial. The Indian industry needs to take full advantage. What do we need to do? The key difference globally compared to Indian industry is the ability to monitor fermentations in detail. To drive fermentations management to best practices and take advantage of the biotech innovation, key analysis needs to be available to both monitor and measure the return on investment. Let's be honest, biotech yeasts are not cheap, and therefore any investment that you make in changing to a biotech yeast, you need to be able to measure and control the return. The technology used globally at the moment is HPLC, high performance liquid chromatography. We actually have the capability to utilize this to assist in trial monitoring, cost benefit justification. So what do you get from HPLC? You can monitor dextrins, maltotriose, maltose, and glucose. You can look at the stress and contamination indicators, lactic acid, acetic acid. You can monitor the level of glycerol, which actually allows you to calculate the efficiency of the biotech yeast in the glycerol reduction. And you can measure the alcohols, the ethanol, methanol, etc. The level of use of these in the USA and Brazil is being used to monitor on a regular basis throughout fermentation the performance of these, and they are able to then track and identify problems ahead of time and look to address it. So being able to look at your fermentation in much more detail other than residual starch or residual sugars and a titratable acid is very, very important to achieve the benefits from these yeasts. So I'd like to now move to a case study. This was based on a trial done in India. And the key objectives of the trial was to show the performance of the bioengineered, which is Fern Boost in this particular case, on Indian feedstock. To show that 100% GA replacement is achievable and to establish the performance of this yeast on Indian process conditions and feedstocks. The secondary objective was to train the plant personnel in the use of the Fern Boost according to the GEAC and the RCGM regulations. This is the safety committee that was formed as part of the approval. So it was to train the plant personnel to follow those regulations. So there was the first step is the standard process. So we looked at this and there was the pre-fermenter volume was 220,000 liters. The pre-fermenter to fermenter ratio was 12.5. The dilution rate was about 1.042, and the conventional yeast was used. The dosage was 150 kilograms per fermenter. The GA was dosed 100%. The pre-fermenter time was 10 hours. And again, the GA to the fermenter was 100% dosage. If we look at what we've done, first of all, we reduced the fermenter volume to 150,000 liters. This reduced the pre-fermented firm ratio to 8.6%. We also almost halved the yeast dosage, and then there was no GA addition at all in either the pre-fermenter or the fermenter, and we reduced the pre-fermenter time from 10 hours down to 6 to 8 hours. So what happened? First of all, we saw that the Fern Boost yeast count was very healthy. It's over 300 million cells, over 400 million cells per mil. And the budding was a very high level of budding, which is very good and effective. Just so you're aware, you can see the budding starting to tail down at the 6-hour mark. If we'd left the pre-fermenter to run to the full 10 hours as previously, this budding would continue to have fallen down. So this is why we cut back the pre-fermentation hours. The pre-fermented percent glucose climbed throughout the pre-fermenter time, and this is showing that the yeast is expressing the GA, because remember, no GA was added to this pre-fermenter at all. And the pre-fermenter gravity trailed down, and if we compare it to the standard, you can see that it's almost no difference. There's no real statistically difference between the two. If we now look at the fermentation gravity, you can see that basically the blue line is the standard fermentation, and it would finish around about the 40 hours. With the Fern Boost, you can see that the kinetics is much faster, and it finished in the region of under 30 hours, which is a significant improvement. And remember, again, there's no GA addition at these points. If we look at the percent RS by titration, we see the same pattern where the control is slower and the Fern Boost is a much faster finish. And again, looking at the glucose by refractometer, we see the same pattern. So what did we achieve? We proved very successfully that 100% GA replacement with Fern Boost is achievable. There was no GA used in the pre-fermenter or fermenter. There was a fast and complete fermentation. We also reduced the PF volume from 220 meters cubed to 150 meters cubed, and this was our first step in the reduction of water consumption. So please bear in mind, part of this trial is not only to improve the process, but it's also to make savings. And a key area for India is water consumption. So this is something that we're very, very focused on. So if we go to step 2, we took a further reduction in the pre-fermenter volume. So again, we reduced the fermentation ratio, pre-fermenter fermenter ratio to 5.7%. We retained the same dilution. We reduced the yeast another 10 kilograms, and we kept everything else the same as the trial step 1. So what did we see? From the point of view of the gravity, everything looked normal on the pre-fermenter. The yeast counts stayed within a range of acceptability, and the budding was slightly reduced, but still well over 60%, which is very, very good. However, what we did notice is that there was a temperature excursion in the early hours of the fermenter, which caused a contamination. So we can see that the firm boost came down here, and the pH definitely lowered, and the lactic acid definitely climbed. This was a concern at first. However, when we looked at the firm residual sugars by titration, we can see that looking at the green one here, that this, bear in mind, the red one is the stage 1 trial, and the green one is stage 2. So you can see that there was almost no difference between the two. And again, showing on the refractometer side, the percent glucose came down and finished well here. So what happened? We showed that the pre-fermenter volume reduction as a second step of water consumption was down to 100 meters cubed. But we also confirmed, maybe a little bit by accident, that the firm boost robustness, that it can work at high fermentation temperature spikes, high contamination levels, and still complete fermentation. So the next thing was to continue looking at water consumption, and we kept the pre-fermenter volume at 100,000 liters, but this time we had no dilution. We put no water into the pre-fermenter and kept everything else the same. So this is the situation, is that the liquefied slurry from the plate heat exchanger, gravity of 1.112, was going into the pre-fermenter. After 6 hours, the yeast cells are over 500 million. That was then sent to fermentation, and then the fermenter was completely filled. So as we can expect, the pre-fermenter gravity was significantly increased from here. So you can see a definite drop, but this is planned because we're no longer adding the water. The pre-fermenter yeast count was well within targets, and the budding was slightly lower, but still over 50%, which is very, very good. Temperature profile, we ended up with a high temperature again. And again, it sort of followed the same lactic acid profiles. And again, it still finished. So all of these ones were basically showing that the fermentation, even under less than perfect conditions, can still perform very, very well. So the last one was that no mash dilution in the pre-fermenter, which was our third step of water savings. So what does that mean? What was the outcome of this trial, and what did it actually prove? So looking at eliminating the external glucoamylase, there was no need to purchase or dose external glucoamylase in both the pre-fermenter or fermenter. This is a direct cost reduction per fermentation batch. It also simplified the process. There's fewer process steps and dosing points, less manual handling, and a lot lower risk of human error and reduced operational complexity. The other thing being is, and this is something that has been shown across multiple countries now utilizing this yeast, that the yeast produces a glucoamylase based on its needs, ensuring continuous and uniform starch conversion. It reduces variability in saccharification performance, and it reduces stress on the yeast, allowing the yeast to perform more efficiently. So the fact that the enzyme production is synchronized with the yeast growth, it optimizes sugar rate availability, which lowers osmotic stress, and it can lead to higher ethanol yields and the shorter fermentation time, which was shown in the graphs. So sustainability and supply chain benefits. It reduces the reliance on external enzyme suppliers, supports the bioprocess integration resource efficiency. And this is showing a benefit overall. And this area is where the key return on investment occurs. So obviously, each company will have a slightly different return on investment depending on what their current enzyme dosage rates are and their enzyme costs, but it is a direct benefit. And this is one of the reasons we have chosen to start with this particular yeast strain, in as much that the Indian industry, not using HPLC, it's very hard to justify and measure the reduction in glycerol and everything else. This direct replacement is very, very simple and obvious. You no longer add enzyme, you no longer buy enzyme. Those are direct cost savings, and that is what is easily measured. The commercial benefits with Firm Boost, and this is looking at optimizing the propagation step and water savings. So 120,000 liters of water per pre-fermenter can be replaced with undiluted mash in the fermenter. Replacing 120,000 liters of water with mash in a 1.75 million liter fermenter is a 6.8% capacity increase. The average firm filling time of about 19.5 hours is equate to 1.23 firms a day. Per day is 147,600 liters of mash instead of water. Per month, almost 4.5 million liters of mash. So if we look at this over a month, we can just see that effectively 2.5 fermenters per month are currently filled with pre-F dilution water, which can be eliminated and filled with mash. That's 2 days of work. So with the Firm Boost technology, you can increase your capacity by 6% without any extra investment of fermentation capacity. Per year, 51 million liters per year, 11.5 months per year is 29 fermenters of mash instead of water. So that's approximately 23.5 days of work. If we look at distillation costs, we get an increased ethanol concentration because we are no longer adding that dilution water. And the higher ethanol content leads to greater distillation efficiency and a lower energy consumption per liter of ethanol. There's a reduced steam demand. Less water in the beer means less steam required to separate the ethanol. This is lower utility costs and reduced carbon footprint. To me, this one becomes more important. The whole stillage volume is reduced by up to 60 meters cubed per fermenter, up to 2,200 meters less stillage per month. So it's reduced load on centrifuges, evaporators, and the wastewater system. So the lower stillage volume means less energy is required for evaporation and drying, reduced wear and tear on the equipment, lower maintenance and downtime. There's potential for cost savings in utilities and waste handling. And from a point of view of global sustainability, it supports sustainability goals and regulatory compliance. The possibility to reduce the quantity of thin slop, which will possibly impact fermentation. So with having less whole stillage, you can reduce your level of recycling and improve your fermentations with less stress. So, conclusions. FermBoost is cutting-edge technology that makes a difference. It's a robust strain that can work in very stressful conditions. This has been proven now. It simplifies the process. There are direct cost savings on GA, and it can reduce water consumption and associated costs, and gives a possibility to increase capacity without any new investments. Thank you. Any questions?
The session is now open. Yes, sir, please.
Good evening, Chris, Richard.
Good evening.
Myself, Neeraj Pratapmal from Kripco Green Energy Private Limited, Gujarat. We are putting 250 KL ethanol plant here. So my simple question is, you are telling me that the biotech yeast having two type of biotech yeast you are producing. So in India, in your PPT, you are mentioning that no external DNA use is the first type of biotech use yeast you are producing, and second one is external DNA introduced. So no external DNA used may be used in India, because in India no GMO yeast is allowed.
So that's not quite true. GMO yeast is allowed. We have gone through the application process and gained GEAC approval for our yeast strain. And we've gone through the process of approval with over 6 customers to get end user approval already. So GMO yeast is approved. It is not approved for ENA or for distilled spirits or potable alcohol, but for biofuels, it is approved, but not a general approval. You have to go through this process of approval and selection and justification of what the strain is. Now, we have 2 strains, one strain that is through approval and one strain that's going through approval. The first strain is the FermBoost, which is the starch-based fermentation. That has a definite GMO, traditional GMO, new DNA added. The second yeast that's going through approval at the moment is the FermBoost ME, which is for the sugar-based strains, and this one is a gene-tweaked system which has no external DNA. So, but both of these are considered genetically modified for within the Indian approvals process, and we have to go through the same approval process for both.
Yeah, and what is the base material for the production of the biotech yeast?
Well, as in nearly every yeast producer in the world, we grow the yeast on a molasses-based feedstock in our process. I'm not quite sure I understand the question. When you say the basis of production, what is your question?
No. Yes. You are correct that molasses based is a raw material for the propagation of the yeast. I am asking about what are the base material you are using for the propagation of the yeast?
In the plant or in our plant?
In your plant.
In our plant, we, like every other yeast producer in the world, we use molasses.
Okay, okay. And sir, in throughout the process, is it any further reduction of urea, or you can guarantee us that the entire elimination of urea can be you can be think while using the GM biotech yeast?
No, the nutrition is still required for this yeast.
Okay.
So if you're a distilled spirits or a potable alcohol producer, you should be using a non-urea nitrogen source such as DAP or ammonia. Most of the biofuels plants are utilizing urea. That need is still working on. If we look at some of the more advanced strains that's used globally, nitrogen requirement is being looked at as one of the benefits to reduce the requirement, but not eliminate it. Now, there are always a certain amount of nitrogen that comes in with your feedstock, and the urea is used to top that nitrogen up to the required amount.
Okay, sir. Yes, sir. Thank you. Thank you very much.
Okay.
One more question. One more question is that in your for the biotech yeast, any protease enzyme is also required?
Well, like always, you can use, if you use a protease, you will reduce your urea requirements. So that's a process decision. If you look at the US-based yeast that we're utilizing, those advanced strains actually express their own protease. So you can replace the protease with those yeasts. At this moment in time, the strain in India, because we are trying to keep the trials and implementation and the cost benefit analysis simple, we are utilizing a simpler strain that is focusing predominantly on the GA.
Okay, thanks. Thank you very much,
Okay.
Chris.
No problems. Any other
Good
questions?
afternoon, sir. Good afternoon, sir.
Hello.
This side Abhishek Patil, sir, from Sangli. Sir, my question is that, actually not question, my doubt is that in this PPT, you are saying that no water consumption in PF. That is resulted to the higher solids in final fermented wash. Okay. Now our existing distillation plants like analyzer column are designed for a specific vapor liquid equilibriums. If higher solids in final wash can affect that vapor liquid equilibrium or any alcohol loss from analyzer bottoms, and further that higher solids in evaporation feed can affect existing design in evaporation sections. And our plate heat exchangers, piping and pumps are designed for a particular DS and specific heat. Our cooling tower is also designed for a particular specific heat and latent heat. So increase in higher solids in final fermented wash can affect this existing plant designs. So what is your view about that?
Okay, my view about that is I will go back 13 or 14 years ago when the whole industry was running around about a 10% alcohol. And we came in with Thermosac and said we could go to 14 or 15%. And everybody gave me exactly the same arguments you've just given me, that it won't work because it's a higher solids and it's everything else and the distillation. But we worked with industry and we showed that by managing your distillation system and managing your process, that the plants can handle the difference. Now, yes, if we go to a trial, there will need to be some optimization. The distillation will need to be balanced on energy and flow rate. The solids on the plate heat exchangers would have to be looked at, but I believe that there is normally enough scope within those plate heat exchangers, so long as you have wide gap plate heat exchangers and not narrow gap, that these would not be a problem. But generally speaking, we've shown throughout the systems that there's a lot of flexibility within these systems. And as I said, we many years ago, we had exactly the same arguments, but now nearly the whole ethanol industry in India has staged up from 10% to 12 to 15% across the board. That's exactly the same argument you're having now.
Thank you, sir.
Any other questions?
Sir, we have two questions in our chat box, and the first question is from Mr. CP Tripathi, and he's asking how much yeast percentage required and alcohol wash can be achieved by use of biotech yeast.
Okay. Sorry, what the one was the alcohol percentage. What was the first question? The first aspect he asked on? Could you repeat the question?
Yeah,
The
sure.
DS,
Yeah,
Chris.
yeah.
The DS. To be honest, I don't have an exact number for the DS. It would probably be, when we run a trial, we would be looking at matching the existing conditions in the plant and then removing the water and seeing and taking the DS up. But it would only go, the DS would only go up by a relatively small amount. The alcohol, this strain we know can work under good fermentation conditions with good monitoring and control, can certainly go up to over 15% alcohol.
Yes, sir. The next question is from Mr. Ramlulu Murugan, and he's asking, sir, if you use GM yeast, what about DDGS quality and is it affect the kettle?
Okay, the DDGS quality is actually, to some extent, there's multiple aspects to this one. It's a more complex question than just a simple is the quality improved. First of all, certainly in the US and Brazil, we have approval for our yeasts to be used as an ingredient for DDGS. So they are approved by the American Association of Feed Control Officers as a part of production of DDGS. Many years ago, when we first started going down this road, we realized that the DDGS would become a very important argument. And so right from the very start, we got every one of our yeast strains approved for the utilization and production of DDGS. So from a point of view of risks to DDGS, there is no live genetically modified material in the DDGS. There is no risk to animals or anything like that. So that risk has been eliminated and agreed by the process of the regulatory boards. But when we look at DDGS quality, what we have to look at is the better the fermentation and lower the residual sugars and the quicker the performance that you ferment on, the DDGS quality will improve slightly. You will get better color, you will get lower Maillard reaction. If you have a very aggressive and high growing yeast, you will get a very slightly higher protein, and you should get lower sugar levels within this DDGS system, which is actually good for the cattle. So good fermentation practice and good performance in fermentation will lead to better, more consistent DDGS. Is that a trait of a biotech yeast? Realistically, no. But in this particular case, with such an aggressive yeast and such a high stress surviving yeast, it enables you to produce on average, a better DDGS because of the better fermentations. I don't know if that answers the question, but I hope so.
Okay, sir. So the next question is from Mr. Neeraj Pratap, and he wants to know the tentative cost of the biotech yeast.
That one I'd rather hand that over to Rajesh. I have not been involved recently in the pricing. And also depending on the size of each fermenter. Rajesh, do you have a price per liter of ethanol or something that can answer that question?
Chris, I can connect with him directly on the pricing part later. Yep.
Okay, thank you.
Yes. The next question is from Mr. Dinesh. Any effect on DDGS sale?
Any effect on?
DDGS sale.
The question I had, or the answer I had on DDGS remains the same, is in as much that there's no regulatory inhibition on the DDGS, and you should have overall, with a very aggressive yeast, a slightly better DDGS in the way of protein quantity and lower residual sugars.
Okay, sir. The last question is from SSPIL Bioethanol. Sir, the biotech yeast is designed to withstand higher TVA condition and facilitate complete fermentation, enabling the gravity to reach nearby zero level. This improved fermentation performance can result in higher alcohol yield and enhanced process efficiency.
Yes. Basically, when we first produced this yeast, we did not anticipate seeing a yield improvement because we were just replacing the GA. There was no process to reduce glycerol. But what we found is with the yeast improving its kinetics and improving reducing the osmotic stress by sort of producing the GA on demand, we have found that in multiple countries, in multiple trials, and in pretty much every case of use, and a yield improvement is associated with this, and it's because of the better fermentation conditions. It's a natural improvement against conventional yeast because it reduces osmotic stress. It reduces the inhibition from contamination because it can withstand the temperature stresses, etc. So overall, it's a better fermentation, and that fermentation has actually shown consistently somewhere between a 0.5 and 1.5% yield improvement on multiple trials.
Okay, sir, thank you. Any other questions from the participant side?
Good afternoon, ma'am.
Yes, sir, please continue.
My question is that higher alcohol is good for ethanol production, okay? But can higher alcohols lead to the final impurities in ENA, or it can affect ENA final quality?
That depends on your distillation system. What we've done in the past is where if we significantly improve alcohol concentrations, what we've done is we've looked to manage the distillation in two ways. One is to look at the scope within the distillation and see that if it can cope with the extra alcohol and keep the feed rate the same. If we find that there's a stress on that distillation system, we can lower the feed rate to distillation and take slightly longer fermentation hours, which is so you produce slightly less distillation per day. Oh, sorry, your increase in distillation per day is slightly less. It's still more than original, but your stress on the distillation system is lower. So it's about managing your distillation system, managing your steam utilization, and looking at your quality. But generally speaking, if you're using your distillation system correctly, there should be no change to the impurities of the final product.
Yes, sir, I totally agree with you. But my observation is that when we go for higher alcohols in fermented mash, there is extra production in technical alcohol. We call it extra production in impure alcohol.
Yes, you may have a slightly increased number of higher alcohols, etc., but it shouldn't end up in your final product. It's like anything. If you step up your process, different aspects. So you may, if you go higher alcohols through adding more feedstock, and you're looking at just say your residual sugars, you will see a very slight increase in residual sugars because the percentage of fermentation efficiency remains the same. But with a higher starting point, you will get a higher finishing point. So things will change with the process. The importance of having a correctly run and controlled trial is to manage all of these aspects and deal with them during the trials and optimization.
Okay, thank you.
Okay.
Sir, we have one more question in the chat box from Mr. Neeraj, and his question is: Is jet cooking required using biotech yeast during liquefaction process?
To be honest, whether you use a biotech yeast or a conventional yeast, the jet cooking is a process decision. It's not relevant to the type of yeast you're using. The jet cooking is, or not jet cooking, is a process really that's focused around the alpha amylase addition and your liquefaction time, your milling particle size, and your target DEs. So providing you don't necessarily have to have that for either system. I don't know if that explains the process. The jet cooking one is a whole nother question of what you're looking at. The one thing I will say about the yeast that we're looking at, we've found that depending what your existing DE is, this yeast can work very well with a DE of around about 12 to 12. And if your current DE is higher than that, and in a lot of cases globally, people are aiming around the 18 to 20, you can also see a significant reduction in your alpha amylase.
Any other questions from the participant side?
Good afternoon, ma'am.
Yes, good afternoon, sir. Please.
Is there any chances to change the sieve size of the floor? Because we are not adding water in PF. So we have to, if we have to put the same sieve size, or we have to put a different sieve size, or until which range it can tolerate this core size and fine size.
Sorry, I'm having a hard time hearing the question. Could somebody repeat the question?
So please repeat the question.
Ma'am, this is
Chris's question is about the particle size, since we are not diluting
okay. Again, the particle size on milling is separate to the yeast utilization. Obviously, from a point of view, depending on the system you have of cooking and everything else, to my mind, typically speaking, unless you have a cold slurry Katzen style design, which I don't think many of you have, the particle size is typically speaking, the slightly finer particle size is a better yield situation, irrespective of what yeast you're using. The particle side is relatively irrelevant for this yeast.
Any other question? So since there is no more question from the participant side, let us conclude the webinar.
I'll stop sharing.
Yes, sir.
Thank you.
Thank you. So we are very thankful to Mr. Chris Richards as a valuable knowledge partner. So please accept a token of appreciation from GEMA.
Thank you.
Thank you all for your valuable time. Good evening, everyone. Thank you for participation. Have a nice day, sir.
Thank you, everyone.
Thank you.